So then the other one is figuring out the flow rate. So that's a flow rate problem. So this is the other type of problem you can have where you're trying to figure out a flow rate given these dimensions, where you know the head loss, you know the diameters, you know the material that's made of. You're just trying to figure out what the flow rate is. This is sort of in the exact same scenario of the last one I did with the diameter that is assumed at all, right? You still write your one equation out. It's a head loss, right? You do this work to figure out all these effective lengths to write out this sum term, which is tricky because you have to keep remembering that each of these F's right? You still write the same equation out for all these pipes in series. You just have to write, it's nasty because each of these F's have their own functions associated with them. So it's like, it's already nonlinear with just this square power right there. But right, these F's are actually, they're actually a function of the flow rate itself. So any type of solver you have to do, you have to program that into it as well, right? There's the Colebrook equation, then there's laminar. They're usually never laminar in these situations though. But again, all of these things come down to inputting a bunch of stuff to calculate what this is, and then asking a computer to solve this. So make this equation true. See, I put like how the friction factors are functions of the flow rates themselves, because the flow rate can be solved for velocity, and the velocity is needed for the Reynolds, right? And then even the diameters in there, but you know that. So that's that part set. But the thing that's not is that this is a function that's a function of this, right? But Jerry wrote out these methods that you could like actually just do this iteration of, calculate it for a guess and then like do the same thing over and over again. But I don't want to limit you to just like that one Jerry method, because as long as you know how to input this equation correctly, where you know the flow rates and just know all the given things, and you know how to program this summation correctly, you then just need to throw this into like an fsolve type program. That's what I use in MATLAB, where fsolve is trying to figure out. Fsolve is this function that's trying to achieve a goal of a function equaling 0. So that's why I write zeros equals this, because if you use MATLAB, for instance, you use fsolve, the function you give it is this function right here, and it would be trying to give you the Q. How you write that function would involve, right? You need to implement how to make all the friction factors pan out here, because these are all equations themselves. But that's it. So there's not really a difference between the pipe sizing problem and the flow rate problem, just as long as you know what equation to plug into both of these things. So that's why I've written this many times. It's head loss, the 8, the function in terms of these Q flow rates. Because you never usually are solving for a velocity. You're usually trying to solve for the flow rate. So writing the head loss equation just in terms of the types of problems you can have, you're always just going to plug in the exact same equation into your fsolve or whatever program you're going to be using. So I think I've written enough times, but I would definitely I would say make a Python or MATLAB program that actually can take care of this summation part right there, where you would give it where it could figure out it would know these friction factors and all these diameters and calculate out this end. And then that would be the function that you would then input into fsolve or the NumPy package. But it's pretty doable because it's just the same. I've just written the same equation many, many times. I've just had different cases of which are the things I don't know. But there's one, if we go back to this type of problem, the easiest one that we did have with no sort of iterations, you could just do it in Excel, and it was so simple, is this question of knowing all the right-hand side and then calculating this side, right? So the easiest engineer solution actually is just to set this up in Excel. Right? It's just setting up such that you pretend that you do know what all the values are. And then you can just, and if this is a very simple one-way calculation where it's just going this. It's just taking a bunch of cell data and spitting out a number. So all these types of questions, right, if you knew what the head loss was, you could just go into your Excel sheet and just change, right? You could change the value of Q and see if you can match your required head loss. You can change values or just the values of the diameters in the cells and see if you achieve this, right? At least you get close enough. I mean, if I'm shooting for, let's say like this that this has to have 30 feet of a head change due to a pump. And you have your Excel chart that just does this summation out really nice and clean. It references one flow rate. And it does all the work to get the friction factors based on that. And then if I can just figure out like the flow rates or some diameter that make it like, I don't know, how about 28 feet? How about 31 feet? I mean, how close do I gotta be, right? If it's just like one guess that gets me super close with my very simple Excel sheet, you won, right? You don't have to do this like, super MATLAB fancy, get the exact number. This would work just fine. And in fact, I do want to point out that Connor had a great idea where, in the end, you're kind of restricted on what diameter pipes you can use because there's Schedule 40 and all those are picked. So his method is he just had a Python program search through ones that would make this work, which I think is a really good idea because if you use like the solvers I have, right, they just give me the actual specific, actual diameters or the point values. But for the diameters, I like the idea of just searching through the Schedule 40s. So, right, and it's the same idea. You're just really trying to get close enough to what the requirement is on here. But that's sort of the layover for, and again, everything we did right now was for the situation of pipes in series. We haven't done the parallel, and that's next.